Okay, the final is, as you know, December 14th, a ways from now. I am holding a review session in here next Tuesday. We'll review the whole course. The final is scheduled for 3 hours, but I don't think it'll take you more than an hour and a half or so. So you can get some sleep afterwards, or if you're sure you're gonna do good, you do a well job, you don't have to show up till 9 if you're sure of it. But most of you, I presume, will show up earlier. What else? Homework, star parties, extra credits. Okay. All right. How many people are comfortable with the notion of a 10-dimensional space? Now, scientists are not comfortable with it, but scientists are just used to seeing the mathematics of it. And, you know, if you say space is 4-dimensional, like relativity needs, it doesn't take as much effort to make it 5-dimensional as Einstein needed for his later theory of gravity and electromagnetism. Then it's not much harder to make it 10 dimensions. Why not? So all those work out nicely. Now, why do scientists need 10 dimensions in this theory? Anybody know? Anybody remember? Why 10? All right, they need 10 because it seems that for less than 10, they can't make it work. And by making it work means here. Your big. Let me have the big one. No, give it here. Give it. Don't leave it there. Give it to me. By having less than 10, they never were able to get general relativity to merge with the other forces. So 10 was the magic number. But then again, scientists thought they played with the mathematics and discovered that 26 works too. What's wrong with 26? I don't know. It's just 10 is simpler, you think. And that's it. That's how you choose a theory. You choose a theory that works in certain fundamentals, and then you see if it works in other things. If it confirms, if it has expectations that you didn't expect, and you can confirm them with experiments. In that case, you have some faith it'll work. For example, when Maxwell discovered electromagnetism, he said, well, I'll add these terms to this equation, and it'll work well. But if the equations, if the effects didn't show up, then his theory is wrong. The mathematics was pretty, but it might be wrong. So in that sense, that's how one makes progress. All right, so today we'll talk about astronomy, about life in the universe. How many people saw this ridiculous movie? Gee, not very many. This should be an assignment. Go see this absolutely insane, stupid movie. There's a whole bunch of these are all descendants. They come off of a mothership. These big monsters are not the biggest ship in the world. They fly up to a mothership that holds them, and they come down and blast these cities. Okay, that's independent. This is a life form. And do you know what brings them down? The American goes in and saves the day. What brings them down? No, wait a minute. You know. I'm sure you know. Anybody? It's so insane. A hacker somehow gets into the ship, and he looks at it and says, "Oh, this is like Unix," and he plays around and manages to introduce a piece of hacked code that is a virus, and the virus corrupts their software systems, and it all crashes. Isn't that cool? Well, anyhow, it's pretty stupid, but anyhow, that's the movie. All right. Now, in this course, we studied all about stars and galaxies. We saw the starlight. We studied the planet motion. We reviewed everything in the universe. The universe is large, and when you spread it out, you see the full universe, the galactic plane, and you can see the spectrum and near infrared. It goes all the way through submillimeter. And only when you get to microwave do you need to turn up the contrast very far, and then you can see the structure behind it. This, in brief, is a summary of what we did in the course. It has been amazingly exciting. So today I want to change tunes. Let's talk about life in the universe. Now, of course, we haven't seen it yet. It's a shame. We went to Mars to look for it, but it hasn't been successful. All right, so the question is, if we see life, we first better define what it is. What's life? All right, well, is there life elsewhere? Is there intelligent life elsewhere? These are fundamental questions we want to know. Okay. Have other citizens, is there technical life elsewhere? Technological life. Now, if life survives on the Earth supposing mankind is still around 1,000 years from now. Doesn't seem, that's reasonable, given our history. It doesn't seem like we're going to survive more than 100 years, but okay, supposing we survive 1,000 years. Now, I bet in 1,000 years that we're going to be half bionic. Can you guess? Lots of things you can be bionic about. You could have an earphone planted in your ear when you're born, a way to speak planted in your mouth. Maybe you'll take out a tooth and put in an artificial way of speaking. And this is probably not that unusual. And so the life that we see is going to be most likely very technological. Doesn't that seem reasonable? It'll be robots, half robots. I don't know. Maybe. Okay, now, next question. Have other citizens ever visited Earth? A lot of people claim they have. Anybody feel that we've been visited? No. Okay. Should we be looking for life? Is it worth looking for it? Look in space by putting your radio's dish out there looking for something. Anybody feel it's worth looking? It'd be pretty neat to discover it. When pulsars were first discovered, they were they were very, very unusual beacons, and they beep, beep, beep. They gave the same signal all the time, beep, 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 and people couldn't imagine what in the world was doing that, and so they named them LGM. What does LGM stand for? Little green men. See, they didn't have any better idea what it was at first. now, of course, we know that they are a rotating neutron star, or we think they're a rotating neutron star that's shining a flashlight at us. But we almost saw intelligence there. Then we saw thousands of them, and that's probably not intelligence. Okay, so we asked the question again, what is life? Of course, we have one example, and we are a carbon-based system here on the Earth. Okay, we know that life is self-replicating. It takes energy from the environment to sustain ourselves. But so does clay. Clay grows in the same way. Clay extracts molecules from the water and pulls it together and makes more clay. Well, doesn't seem very sensible to define that as life. So you have to be a little careful. Now, we know life comes in cells, but maybe life elsewhere does not come in cells. It would be very interesting to find something that doesn't have cells. We have a blob of protoplasm, no cells in it. That'd be pretty neat. Sort of like a giant. There's a very old movie of the thing that falls in, comes to the Earth on a spaceship, and then it gets on somebody's hand. The Blob. Anybody seen The Blob? It's an amazing movie. This blob gets attached to a man's hand, and the doctor can't get it off. It grows and grows and grows, consumes the man, then consumes the whole town. It's a pretty scary movie. It's an original science fiction movie. You should look for that online. I'm sure it's on YouTube somewhere. All right, so there's no cell. I don't think it had cells. Viruses, units of the cells. Viruses can't live by themselves. They don't, they have to invade a cell to replicate. All right, what is life again? All right, well, is life really require a carbon-based system? You can imagine life is silicon-based. Why do I say silicon-based? Everybody remember chemistry? A little bit of chemistry. Carbon can form units of can merge or form molecules of 4 units attached to the carbon. 1, 2, 3, 4 on any side of it. All right, and it's the most reactive, the element that really can form anything. So carbon's really the center of life on Earth, but silicon, just below it in the periodic table, also can form 4 molecules attached to the carbon, or the silicon on the Earth. But unfortunately, silicon chemistry is not as rich as carbon chemistry. At least we don't see it as rich. But if life were in the form of computers, it would be probably silicon-based. After all, silicon forms the basis of computers. Okay. But now, other elements. Earth requires water. So carbon-based with water is, of course, how our life formed. And we think that's necessary. Okay, so now, this is not a problem since carbon, nitrogen, oxygen, hydrogen, and water are very, very common in the universe. We're sure all these are made in all types of stars. Massive stars spew out this junk and makes all the ingredients necessary for life. And furthermore, we see that organic compounds exist in radio. You observe radio observations, and you see the signature, and on some of these systems you find an awful lot of alcohol. A lot of alcohol. And that's fairly complicated. What is alcohol? Who's the chemical notion of alcohol? Anybody? What is it? It's hydroxyl. Okay. All right, so it is, and that's seen in space. Now, a lot of chemicals are generated there. We don't think anything complicated like that would form life is generated there, but, you know, that's, in science fiction books it happens, but not, at least we don't think it happens in reality. All right. So life needs amino acids to form, and a lot of amino acids are fairly simple, and they can be formed in space. So there's no problem with forming them in space. You rearrange them, and you might make complicated molecules. That's unlikely, in my opinion, but okay. All right, now, emergence of life on the Earth. The conditions for forming life are common. It took a long time for the life to evolve in the form of cells. And it's, you know, we don't know exactly how it happened, but it happened early. It happened probably after 1 billion years. The Earth was still hot, and it's formed life already. And it's pretty amazing to think about it, because the Earth at that time was very hot, and it was not at all unusual. It could have been like that in millions, billions of planets around the galaxy. Okay, how did we make DNA? Well, that took a long time, I presume. We don't know how cells emerged. And the final question is, what is the quote-unquote moment for life to exist, to emerge? It's unclear. It's certainly not a thinking life. All right. All right, so life formed under very, very primitive conditions, and it evolved early. Okay, so now the first question you ask is, where was life born? Since I was a child, people said, well, life is born on the ground. The ground's got flashing lightning on it. It's got water that's reactive. It's got sunlight, blah, 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 all that stuff. But that might be completely wrong. The life could have formed on the surface, could have formed in space. That's a comet. And it could have formed deep underground. Probably the life could form. Now, have you seen the movies or the short clips of the amazing life seen in the fumaroles underwater? They're deep underwater. Who's seen these? Most of you haven't seen them. All right. The volcanic area on the Earth is right along the split of the Earth where North America is separating from Europe, for example. That split goes all the way down the Earth from Iceland all the way to southern South America. There's mountain range there, and a lot of the mountains are spewing volcanic debris, volcanic whatever. And the water is warmed. And the life is very, very prevalent all over there. There's clams and all these other things. Now, what it eating? You say, what's it eating? It's eating a primitive bacteria that is growing in the water. So the life that might have formed in something like that situation are these primitive bacteria. This is probably extremely common in the galaxy. All right, so life gets formed somehow. It later makes RNA. Somehow they make cells. They make cells in the RNA, various genome activity, primitive cells, and then later they get modern cells. Now, this doesn't happen overnight, obviously, but the Earth, it was such a laboratory to experiment and take variations. The variations are gigantic. And people who don't think that life formed out of nothing haven't factored in the fact that they had 4 billion years to do these chemistry experiments. That's a long time. You can't, you think of 1 billion years, that is forever in our lifetime. That is forever. It's warm. You get different chemical reactions that may not be very common. You've got a whole ocean where it's happening. And this undoubtedly has led to primitive life. The primitive life goes around. If, for example, look at our cells. Our cells include we're eukaryotic cells, and they include little globules. What do they call them? What are the globules called in the cell of a different? It has its own DNA. Mitochondria. All right. Now the mitochondria are in every cell, but the mitochondria are probably a primitive bacteria or something that was eaten by the cell, incorporated in the cell. So this didn't happen. I mean, it happened randomly, but then the cell realized it's more advantage to have it happen. It happens, and the cell reproduces more. Such a thing with all these improvements just lead to a further and further gain. So a long time for this to occur. All right, now life as we know it. Here's this is undersea. The life forms in here, is blowing out these fumaroles. Now this life there's no oxygen in the vicinity. Life is not dependent on oxygen. A lot of life is poisoned by oxygen. And the primitive life almost certainly would have been poisoned by oxygen. So primitive life, the issue of what you depend on there, turns out that there's some reaction that eats sulfur dioxide, which is being emitted by this fumarole, and reduces it. It takes the oxygen in it. It gets some energy from that. I don't know exactly what it does. And then has waste sulfur. And the sulfur just accumulates in the cells. Now, there's very primitive life seen in these pools. This is at Yellowstone. Here's a walkway. And you can look and you see the pool bubbling up from the deep, bubbles up from the hot springs underneath it. The colors are from bacteria, but the stuff in here is it's a very different bacteria. Bacteria eukarya archaea. Everybody learn this? Division of life forms on the Earth? Who knows this? This is something you would learn in biology. Anybody seen this? 1, 2, 3, 4, 5. The rest of you haven't taken biology yet? Don't you do this in high school? You remember this? Now, when I was in high school, archaea had not been discovered. All right, that's a while ago. All right, and so we knew of two life trees, branches, bacteria and eukaryotes. We knew about these archaea. We'd heard of them, but we thought they were a type of bacteria. They're not. Why aren't they a type of bacteria? How do they classify them now? Anybody? How are they classified differently? Okay. And what difference is the bacteria from the archaea? All right, there's some, I don't either. But you examine these animals, or these little things, at the cellular level, and they're very, very different. They're not even closely related. If we discover life on another planet, it will most likely be an archaea something in archaea, because that seems to be the basic life, the mother, the first life was probably of that form, and this is the type of life that survives. This is the type of life that likes these fumaroles and this hot water. This is in boiling water. You can't imagine life forms surviving in boiling water. But archaea do. And they have, here's what, thermoplasma, I guess that is. Thermococcbi, I don't know. All these crazy thermos, whatever. Here's green bacteria, purple bacteria, cyanobacteria, goes on and on and on. They're all different at a sub-level. This tree is meant to separate the different animals at a time when the cells look different, really sufficiently different. And meanwhile, humans aren't even on the tree. Humans are just up in the corner. Animals, here we are. Animals are one tiny branch of the tree. So the animals, what that means is the animals are genetically about the same. But all these life forms here are different. Fungus is over here, is one of these. All these things you haven't heard of are different. And if we find anything out in space or on Mars or anywhere, it's going to be even weirder than this stuff. Probably very weird. Okay. That'll be interesting. I don't know. We'll see. Okay. The issue is the sun has been getting hotter and hotter, and the temperature of the Earth goes up and up and up. This is the sun's output. It's gone. The temperature of the Earth is no, that's not the sun's output. Anyhow, what is that again? All right, here is the luminosity of the sun, and when it started 4.5 billion years ago, it was only 80% or 70% of its present luminosity. Why do you think the sun has got brighter in all that time? What's changed in the sun to make it brighter? Anybody? What do you think it is? Yeah. Different types of fuel? Well, the sun, remember, is still burning hydrogen. But it's burning hydrogen in the presence of helium, its waste product. So hydrogen burns, makes helium. And as the helium accumulates more and more and more, the luminosity of the star goes up. And that's what the issue is. Okay? So the sun's going up. Meanwhile, the carbon dioxide is going down. Here is a plot of the carbon dioxide going way down. All right? And it is huge all that time here. This really heated the Earth. And this is in bars. A bar is, remember, the pressure of the Earth is 1 bar by definition. So this thing, the carbon dioxide, had a heavier pressure than that. And it's been falling as the Earth has aged. This cools down the surface of the Earth and maybe makes it easier for life to make progress. Okay. Now, if you look at the stars and try to classify, you ask, where's a star warm enough for water not to be frozen? And here, for example, is a G2 star. This is like the sun. Venus is here. Earth is right in the middle of the habitable zone. Mars is on the outside. This zone is the region where liquid water can exist on the planet. And Earth is right in the middle of the habitable zone. That's convenient for us, obviously. On other stars, M0 stars, obviously the habitable zone is very close to the star because the sun's output is not sufficient to heat the planet up. So M0 stars, M stars, recall, are faint red dwarfs. That star is not putting out much heat. However, these stars live forever, basically. You know, since the beginning of our universe, 14 billion years ago, M stars have formed, can be 10 billion years old. If we encounter one that has life right there, close to it, it might be very, very advanced. It's had, after all, 10 billion years to evolve. That's pretty good. On the other hand, there are F stars, a little brighter than the sun. F0 stars, if they have a planet out here, it's big enough for the planet, for the habitable zone to be moved out. So if you find planets further out, maybe they have life as well. We don't know. All right, now the habitable zone is plotted as a function of the distance from in astronomical units from here's a star. Here's an M star, K stars, G stars here, like the sun. And we're right in the third planet from the sun is there, and we are in the habitable zone for a G star. But if you get too close to the planet, like can happen on some of these M stars, if you're too close to the planet, you are tidally locked. Remember what tidally locked planets are? Who remembers what tidal locking means? one side always faces the planet, always faces the bigger planet. EO could be, like the moon is tidally locked to the Earth, always facing the same side. So the tidal locking would be anywhere below this curve. You have to be outside of it to not be tidally locked. That means M stars are tidally locked, and you're close into the star, but you're tidally locked to it. Can life form in those circumstances? I don't know. It's different. Can you imagine Earth trying to form life if it were tidally locked to the sun? What would the Earth be like? Yeah. Right. One side would be frozen solid on the back side, and the other side would be hot as hell. So in the middle would be the conditions for life, or the conditions where it's moderate. Is that good? Are those good conditions for intelligent life to form? I don't know. Could be. All right. So how about looking closer? We don't want to look so far. It'll take forever to get to these other stars. It's possible we could look for life not only on Mars, but you might look for life here. This is Europa. Europa is a gigantic ice cube on the outside. But underneath this layer of ice is liquid water. The liquid water is salty, and they know that because it supports a magnetic field. And there could very well be life in there. The life could, for example, survive on the fumaroles coming up from the inner planet. Does that sound reasonable? How much money are you willing to spend to find out? Anybody? Not enough? You're not interested? Is that? Nah, okay. How many people want to spend $1 billion? $4 billion? No? No takers here? Geez, you guys better not become senators. You'll never vote money for NASA. They might, it's possible. So Europa might have, it has an ocean of liquid water, and tidal heating keeps it warm, plus the fumaroles is born with. Okay, so, maybe there's a big life in there. Now, there have been some thoughts that we could explore this by landing on Europa and then drilling through there, drilling through the ice, and examining at the bottom of the ice, send a flashlight, and look around for swimming fish, for example. Does that seem... That's pretty crazy. You might find life that way, maybe, but probably not. Okay. These other planets, Ganymede, Callisto, also have subsurface oceans, but their heating is weaker. They're probably not life-forming. There could be life on Titan. Titan is crazy. A thick atmosphere and oceans of methane and ethane. Can you imagine life forming in methane? That's a fairly complex, ethane's more complex molecule. And that might be a place for life to form. Here's Europa. This is the surface, cracks, and all this is that's showing how the Europa is covered in ice. This is actually ice, and it came together and came apart. This was tidal, probably. Titan has haze, chemicals, and junk raining down to the surface, but the surface is only 92 degrees Kelvin. a very cold life, if it exists at all. All right. So the more mass of the star, you know, the bigger the habitable zone. If it's like this, if it's this type of star, lasts longer. However, this star lasts. The age of this star could be 10 billion years, or 50 billion. No, there could be 10 billion year old stars with life in them. It was habiting here. So that's a nice. You know, that's probably a good place to look. The first place people looked is obviously Mars. Okay, so people have looked for Mars. And Mars has not seen, you know, there have been lots of stories. Who's seen the story, H.G. Wells' story? The Martians send a ship, what's that story called? War of the Worlds. Anybody seen that movie? The new one with Tom Cruise in it is, you know, an interesting movie. It tries to, well, it's a little modern. The original one, I don't know if you know about H.G. Wells was the reader. He didn't write the story. Or who was the writer of War of the Worlds? Oh, same name. Okay. All right, that's why I'm confused. All right, Orson Welles, when he was younger, in the 30s, read this story over on the radio about the coming of this Martian invasion. And people in the country heard him on the radio and didn't realize he's reading fiction. They thought it was a news broadcast. That'd be pretty neat. You know, reading about this. Who's read that story? You guys haven't? Oh, man, you should read the story. It's wonderful. It's wonderful. Why the Martians come to Earth? Anybody? Yeah. Yeah, it's getting too dry. And so they're going to come to Earth and live. And they realize they're going to have to get rid of whatever's this crummy life form on the Earth. Sorry? Yeah. What kills them? Bacteria, which they didn't figure on. All right, the bacteria have a field day eating them, and they die. All right. So now Mars is clearly could have formed life. We know that Mars was wet, and it had a lot of water some billions of years ago. How do we know that? Now, liquid water still exists, we think, and might exist. So there probably was water ice. There is water ice in the North Pole. Okay. Here's a lander sent in 1976, a picture of it. And this is its foot. Lots of rocks on Mars. Those are volcanic rocks. So they've looked for it. Now, when they looked for it, they basically took a scoop of dirt and put it into what amounts to chicken soup. Basically, the same thing. They put it in chicken soup, and they said, well, if there's bacteria in there or something, it'll eat the chicken soup and give off waste products. The waste product could have been carbon dioxide, something like that. That's our waste product. So the experiment had a scoop of, the ability to do this little experiment. They scooped up some dirt, put it into a bath, and gave it chicken soup, and then they measured looking for waste products. And it was successful. They saw positive evidence that the thing was successful. Now, this was in the 1970s. You were he didn't exist. But this made a tremendous, tremendous excitement. Mars had all the attributes of life, or at least they thought it did. But then they realized that's not right. And why isn't it right? It's because Mars also has on the surface a lot of things like oxygen tetrachlor. What is that? Carbon tetrachlor. No, not carbon tetrachlor. Peroxides. Peroxide of water is used as a bacteria is activated water. What does peroxide of water contain? Anybody? It's a stable chemical on the Earth. I believe it's made out of H2O2. And this is a pretty good, you can put it on a wound and it clears it off. It burns. It's really a burning liquid. And it kills bacteria. The problem was that Mars has no atmosphere. And because of that, the planet absorbs cosmic rays, high energy particles, and they blast into anything and make a bit of peroxide. And there's nothing to make the peroxide go away. So when they realize, oh, we've got peroxide in there, then the experiment's not valid. Okay, that was a shame. All right. Mars only sampled the soil in 2 locations. There were 2 Viking landers that both worked. They landed at different places, and so they sampled the soil at each place. And that's not very much. You'd like to have a roving device. All right. There are Martian meteorites, rocks that are seen in Antarctica, and they contain lots of these rocks are known to be Martian because the composition of the rock is not from the Earth, and they must have been Martian. So what has happened is Mars was hit by a comet or something, an asteroid blasted Mars and threw off a few rocks into space, and one of the rocks, at least, made its way to Antarctica, where it was picked up. They saw complex molecules. Don't ask me what they are. All right. The analysis suggests it was old, landed on Earth 13,000 years ago, contained complex molecules, and they said this is life. So there was life on Mars. And they saw what they said was fossils of nanobacteria. And there were claims. One claim was that these nanobacteria were very small, very much smaller than nanobacteria seen on the Earth. An argument was given that, well, that's not practical. If you think about it, the nanobacteria on the Earth have a certain size. As life evolves, they might get smaller, but they're unlikely to be born small, because that means efficient birth, and they don't think that's not practical. So that's not, various reasons. This was really debated at the time, 15 years ago. All right, made the news. This might be formed by other means. And they conclude, finally, that this rock is contaminated by Earth stuff. All right, so that's not a good example. This is a good example. Okay, you're looking for life, and you find it on a hillside in a Cretaceous boneyard. This is along the Colorado River. This is in Utah, in the Colorado River, right nearby. Has anybody been there? It's a neat place to go. It's just astounding there. all these giant fossils. It'd be nice to find that. I don't think we'll succeed, but that would be nice. All right, so life on the Earth existed very, very long ago. Earth's period is divided up in, this is 4.5 billion years. 4.5 billion years down to 0. First is known as the Hadean, the Archean, the Protozoic, then finally the Phanerozoic. Well, I don't know why these names are there. All right, so bombardment of the Earth during the Hadean period, that means hell-like. They have some evidence life was formed here. I don't know about that. Microbial bacteria exist in this area, they think. And here is where oxygen is built up in the atmosphere, in the Proterozoic. What does oxygen in the atmosphere mean? What does oxygen in the atmosphere mean? If you see a planet with oxygen in it, what does it tell us? Okay, let's see anybody else. Anybody? Yeah. There are plants. Oxygen is not natural. It is made by life. So that is a key that you can look for. Look for oxygen in the atmosphere of the object. And that will tell you if there's life on that planet. So obviously, you can do this from the Earth. You can examine, well, not yet. You might be able to examine the atmosphere of different planets to decide if they contain life. Now, this Phanerozoic is divided up into all this basis, starting 550 million years ago to today. Carbonation, the Cambrian period, Ordovician, Silurian, Devonian, Carbonation, all these things. They all have different meanings. They're ended at different times. Like, for example, the time between the Cretaceous and the Tertiary time is noted by an event, the Cretaceous-Tertiary event. That is the date that the Earth was struck by a comet. All right, and that killed everything. All right, so the fossils are very different here compared to here. And of course, man was born in the last million years. He's barely on this scale. All right, there's a Cambrian explosion. We know that at that time was when the life forms on the Earth really, really, really exploded into different forms. This is also a time when the Earth was covered in ice and snow. It's known as the snowball Earth. The entire Earth is covered in snow. That changes its albedo enormously. That means its albedo is the reflectivity of the Earth, and that kept the Earth cold. The Earth was permanently cold or in an icebox. But it wasn't permanent. What ended? Anybody know what ended those snowballs? Got the Earth is completely covered, and it does not, and completely covered in ice. The ice reflects the light, and the condition on the Earth is very cold. Yet it ended. How did it end? Yeah. The greenhouse effect. And what was making the greenhouse? Well, life on Earth was sort of under the ice. It wasn't able to release anything. Yeah. What? Volcanic reactions is what we think did it. The volcanoes are real good at spewing up carbon dioxide. And this time there was nothing to absorb the carbon dioxide. No plant life would absorb the carbon dioxide. It was accumulating in the atmosphere, accumulating a long time until the atmosphere held the heat in and eventually melted the ice. Okay, All right, so everything, animals land on the land, 400 and some million years ago. Not very long, according to the age of the Earth. Okay. Now, if you look at the spectrum of planets, for example, this is the spectrum of Venus. Venus shows, this is in the infrared, 10 microns, 20 microns here. At about 14 microns, there is a strong absorption band of carbon dioxide. And Venus shows it very strongly. The Earth shows it too. But the Earth has a feature that is not present on Venus, not present on Mars. Mars shows carbon dioxide, but Earth shows a feature of oxygen 3, ozone. Ozone is basically made from oxygen 2. The oxygen 2 is bombarded by cosmic rays from outer space, and eventually part of it converts to ozone. That's 3 molecules of oxygen together. This has a feature at 10 microns or so, and that's something to look for. If we see ozone on a distant planet, this is the easiest one to look for, in fact. If you see ozone on a distant planet, that is a sign the planet has life because it has oxygen in the atmosphere. Pretty neat. All right. We're not likely, unfortunately, we can't do this yet. The stars next to the planets are way too bright compared to the planet, and it's too difficult to get a spectrum of it. So in the glare of the parent star, it's just too hard to get a spectrum so far. But stay tuned. It may be possible in the next 100 years, I think. Okay. Now, we know the planets exist. The Kepler mission measures the light curve of looking at all these Earth-like planets. The sun is 100 times the size of the Earth, so the Earth obstruction is only a part in 10 to the 4th of the light from the planet. Yet in spite of that, Kepler has seen this dip on many planets, and now they've identified that many of the planets exist in the habitable zone. But they can't get a spectrum of them. They're too faint, and we're very far from having the technical capability to measure the spectrum of them. Even though we have hundreds of objects to look for, there are going to be more in the future, but it'll be amazing if it works. I mean, that's the dream of NASA in space, and I don't know if it's going to happen. All right. Ozone would mean there's life on the planet. All right, life. Have you seen this movie? No, what's this movie called? E.T.? And this one? Man in Black. If you haven't seen these movies, this one is really worth seeing. They're all worth seeing. This is Independence Day. Okay. This has an interesting premise. Okay. Anyhow, have the aliens already found us is the fundamental question. Have we been visited by the aliens? Well, probably not. But it's fun to speculate. Have they found us? Now, the trouble is, it'll take too long to go a long ways. It'll take 50,000 years to go to the nearest star. If we're going at normal speeds, 20 kilometers a second, we could go this speed now, but going faster is pretty hard. Too expensive. If you're going fast, it's still taking a long time. and if you go higher energies, if you go higher speeds, we don't have any idea how to do that. So it's not easy to make our way to a distant planet. So therefore, unlikely that we've made it. But now there have been various ideas on how to get there. One of the ideas is to send robots. Send robots that are capable of replicating themselves. Now, you think about it. A robot makes two of itself, then they make two of themselves, and they make two of themselves, and very soon you have an explosion of these robots in space, all of which are making life, and you've got a swarm of robots. They're programmed to signal back to their home planet or something. But is that possible? Can a computer eventually be clever enough to fabricate itself? I don't think anything can do it now, but that's something to think about. You know, we're talking about life that could be incredibly advanced over us. It might be possible in one of these advanced life forms. All right. All right, no artifacts. There are none on the Earth. You know, always when they land on the Earth, they contact the local farmers. They make crop circles. They make other things out in the desert that can only be seen by somebody from Earth. There are things in the South American deserts, the Anasazi. They have these giant stone formations that make up makes up something that was signaling to somebody in space. You can't see it from the ground. But from space, you can see that it is a man or something. This was made by people thousands of years ago, signaling their gods that they're on the Earth, I guess. But they're not. They're unlikely to be made by aliens. The issue is, if aliens are going to visit us, why don't they land on the White House lawn? I mean, that's really where they should land. So far, they haven't done that. Okay, but now, suppose we're sending signals. You know, we could send signals too. It's possible by sending signals, they can eventually receive them, and then they'll answer back. Now, for one of the most ridiculous experiments done is the Arecibo Observatory in Puerto Rico. This is the primary mirror here. It's formed in a bowl of the Earth. This is 1,000 feet across. It's formed in a natural bowl where it gets a circular shape pretty easily. So they're sending radio up there. One of the things they sent is this pattern. What the hell? This is a prime number by a prime number, prime number by prime number, and we send a signal out. They just encode the bits and send out the signal. What the hell does this say? Anybody read this pattern? All right, here's man. Here is our DNA, somehow. Here is, I don't know what this is, but they're supposedly showing it's not a random pattern. Oh, this is no, this is not sent by the radio receiver. It was sent by these satellites. All right? The satellites, that last picture was a picture of the satellite. The satellite had on it these license plates. It's about the size of a license plate, and this was scribed on that on the satellite as a plate you could take off and put it on the car so people know who you are. And it's supposed to show, this was Pioneer spacecraft. It was launched in the 1970s. Now, what does this one show? What do you think this shows? Solar system. The third planet sent a ship out. They've got a boost from the fifth planet, that is Jupiter, and is sent off in a direction. This is the spacecraft. That's a picture of itself. Here's the intelligent people shown next to the spacecraft to give them a scale. What is this? This is absolutely crazy. What do you think this is? You're intelligent, you're intelligent beings picking up this thing. What is this stupid thing? This is the Earth at the center, and this is the distance to nearby pulsars, showing where they are. I don't know. Now, if you don't like that, maybe you like what was on the Voyager 1 and 2. These were the satellites that went by the outer planets and got real close to Neptune and took all those amazing pictures that we showed earlier. Here it is, mounted on the device. This is a phonograph record. Can you believe it? So they don't, I suppose they figure if anybody's going to pick this up, they must know it's a phonograph record, or they know how to decode it anyhow. The phonograph record contains music, readings, images from Earth. It also contains this image again. This, I think, that's hydrogen spinning up. I don't quite know. And a bunch of other junk. Now, the real trouble with this is, these things are just in our neighborhood. They're not going to get anywhere for billions of years. So, we can send this out, and there's nobody looking for it, unfortunately. But that's our effort. All right. Damn it. Let me skip everything. All right. When life forms in the galaxy, it probably forms here in the green area. Because if you're too close to the center of the galaxy, the radiation produced there is too high. You'll just be zapped by radiation in space. If you're out here, the heavy elements are too rare. So this ring of life has heavy elements and yet doesn't have too bad a radiation environment. So that's probably where life is formed. Habitable worlds. Now, habitable world does not necessarily have life. It's just a place we could move to someday. It's old now. Constraints, it has to be old enough, in stable orbit, has to have habitable zone. And there are billions of planets that could do this. Okay, now, I will spend the rest of the time, I'm sorry, this is going to be a little late. The probability of finding intelligent life is written down in the Drake equations. Drake is a man, a professor at Santa Cruz. How likely is intelligent civilization in the galaxy? So the number of intelligent civilizations is proportional to the number of stars. Probability the star has the right characteristics. Probability is planets on the star. Probability it's inhabitable. Life, complex, blah, 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 intelligent, radio signals, times the lifetime of the life. All right, now, here they are. Okay, I want you all to vote. Somebody come down and write on the board what the votes are. Who wants to volunteer? You want to volunteer? Just write on the board. Okay. Number of stars to start with. Whoops. You can't look at that. That's my numbers. Okay. The number of stars is 4 times 10 to the 11th. Okay. Probability, the fraction of stars with the right characteristics. What fraction of the stars in our galaxy have the right characteristics? What do you say? Anybody? It has to be, say, a G star. A G star is about 10% of stars. Okay? Right characteristics. Why don't you just write to the right, but 1/10. Put it to the right, because we're going to have a lot of all right. All right. No, right of character, just here. Just right of it, not down. And write it as don't write it as fraction, just write decimal. Okay? The probability the star has planets. What do you say? 100%? 50%? I'd say 100%. Okay? So let's, planets, 100%. Probability that planets are in the habitable zone. They have to be in the habitable zone to have water. 40%? Okay. Okay. Now, probability that simple life formed on it. It's the planet's in the habitable zone. It has, it's warm. You know, it's warm enough. I'd say 100%. 100%? Who likes that? Who has a better number? 50%? 90%. Okay, 90%. Simple life. All right, now, this one's harder. Complex life. That means it goes beyond the real simple stuff, making intelligent things. What's that? What probability is that? Come on, this is science. We're doing science now. Give me your best guess. 10%. All right? All right, now, probability intelligence. Probability intelligence develops out of this complex life. Didn't you learn anything in sociology? Give me a number. 1%? 10 to the minus 3? 10%. Okay, let's be optimistic. Okay? Then the probability that this life is so sophisticated it'll send out radio signals to us. 5%? Is that 5%? Sorry? Okay, 5%. This one is hard. Lifetime of the intelligent life divided by the age of the star. I'll give you the age of the star. Let's say it's 5 billion years, just like the sun. So how long will we live? 1 million years? You like that? 5 million years? Sorry? Very unlikely to live. It's unlikely we're even here. Is there intelligent life on the Earth? I don't know. Well, let's go for a long-lived life. 1 million years. Okay, or 5 million years. It makes the numbers rounder. 5 million years. Lifetime over age. That's 5 million years makes that 10 to the minus 3. Okay. Somebody got a calculator? Somebody got a calculator? Tell me what the answer is, the sum of all these. Multiply them all together, like this. Okay, multiply them all together. This will tell us the number of intelligent beings out there trying to send us signals right now. I don't think that's right. Did you multiply times the number of stars? 70,000, okay? One number, 70,000, with these optimistic statements. That means there's 70,000 intelligent life forms out there trying to say hello to us. So we should look for them. Now, we said this life form is going to live a million years or 5 million years. I think we better stay away from them. We better not advertise where we are, or they're going to... Can you imagine seeing a life form that was intelligent for 5 million years? Whoa. I think we better be careful. And, you know, that's what's out there. All right, now, for the end of the class, I'm going to hand Isaac, can you give me a help here? I've got to hand out these instructor evaluations. Can you take some of them? Split them up with Isaac. And okay, why don't you split them further so do this faster. Oh, here's Eric. I'm sorry I'm so late. I forgot this. Okay, so everybody don't worry about the final. It's not going to be any harder than what you've taken so far. Remember, I'll put the equations on the front of the final. All right. What else? By the way, has anybody heard of SETI? There is a way to search. If you want to follow SETI, this is something that runs on your computer when it's while you're not doing anything. It runs while the computer is idle otherwise, and it searches for life. So you can follow that. Search for extraterrestrial life at home. This is SETI, and it will do it. So there's 70,000 life forms out there. Why not see if any of them are signaling us? Okay. So, is this enough? Probability of success is difficult to estimate, but if you don't search, we'll never find it. So go out there and search. Everybody can search on their computers. This is written by two scientists in 1959. Okay, that's the end of the course. We've covered everything. All right.